Hey sharks! Today, first of all, ignore the production on this video, the budget was low, but today we'll be talking about orbital dynamics and stability. Stoked. So just as a quick overview, I'm really hoping you can see this. The focus of this project would be on three main things: period ratios, gaseous influence, and orbital spacing influence on the stability of exoplanetary systems, and potentially what that could mean for the habitability of those planets and those systems. So, just as a little bit of background, again, I'm really hoping y'all can see this. For period ratios, the goal with that one would be to analyze system formation and evolution over time so that we can get a better idea of how the stability might change. For the gas disks, their influence could be modeled using in-body simulations, and this would tell us about the role of gas disks and planetary system formations and the stability regarding that. And the last one would be orbital spacing, and this would tell us about the dynamical processes shaping planetary systems and their orbital architectures. And let's just take a second to appreciate how beautiful these graphs are. Wow. Okay, so the first one would be period ratios. So the way that we would analyze this, ideally would just probably be using Kepler data, which is what Lassar did here for these two plots. And then following that up with an in-body simulation that would probably look something like this, to model the dynamical evolution over time. And this would help us define the stability criteria and analyze the effect of period ratios over time. The second one would be gaseous influence. So the gas effects on orbital dynamics, including eccentricity, dampening, and migration, would be a main focus on this one. And this could be studied to help us understand how this gas disk affects the stability and architecture of these planetary systems. And ooh, this is hard to do upside down. Hello. Here's a little video for y'all. Wow. As you can see here, the gas plays a huge role in all of this. Kind of playing as a little nebula to all these little planets. Wow. Ooh. I should have put music behind this. Ooh, the little burst. Okay, you get the idea here. And our last one would be the spacing, the orbital spacing between these planets. And for the study of the orbital spacing influence, ideally, the initial conditions for these planetary systems would be from real observational data. And we could model these over time. It's similar to a superplanet crash here, which I've included a picture of if you remember this from class. This is your reminder to go play superplanet crash. Similar to that, less emphasis on the mass of the system as much as the spacing specifically here. And then studying the orbital dynamics of these systems with multiple planets is a really huge focus on the stability of this project, the orbital dynamic stability in general. Because as we know, the more bodies you add, the more complicated things get, as we can see in Superplanet Crash. So your reminder to go play that. So just to wrap everything up, this project will be focusing on period ratios, gaseous influence, and orbital spacing between these planets to see how we could model the stability over time and just better understand the stability of these exoplanetary systems over time. And hopefully from there, we could understand some better, more solid criteria on habitability for these planets and their systems, which could tell us about potential life on these planets. So if the system could be stable for a long time, it might have a better chance of hosting life, and maybe there's aliens on these planets. And that's what I leave you with today, aliens. Thank you so much for watching. Shout out Orbital Dynamical Systems. I really like this project. Thank you.